So here we're given that the half-life of radium is 120 years. So we want to find a couple things. We want to find the exponential decay model. We want also, if a certain experiment accidentally released 40 grams of radium, how much will remain after 60 years? And then lastly, following up with the previous question here, right, how long will remain after 300 years? Okay. So this is half-life, which it's still exponential decay, right? But it's a little bit different. Okay, so here we're going to use the model A equals A naught A to the T power. Right, so A naught is the initial population. Okay, A is the population at time T. Okay, where T is definitely essentially the half-life. Okay, A is going to be the rate here. Okay, the rate of decay. Okay, so we want to find a model. Okay, now the key is that this is half-life. So what does that mean? It means that depending on the initial population here, right, 120 years later, right, then A should be half of this. Okay, so what do we mean by that? It means that A divided by A naught, okay, equals A to the T power. Okay, but this quantity should be half. Okay, so we get that 1/2 is equal A to the 120 in this case, because the half-life is 120. Okay. Now, how are we going to solve this for A? Okay, so there's a couple ways to do this. Okay, but what I'm going to do here is I'm going to take, okay, so this is the 120th power, right? So actually, if we take the 120th root of this guy, okay, and we should take the 120th root of both sides actually, right? In this case, these cancel out, so we just end up with A. Okay, now your calculator should be able to handle this. Okay, remember, it's not the square root of 1/2. Okay, it's the 120th root of 1/2. Okay, so by doing so, we get 0.994240. Okay, I'm just going to round this to 6 decimal places. So this is A. So that means then that our model is A equals A naught, okay, and then 0.994240 to the T power. Okay. All right, so now the second question says, well, let's say a certain experiment accidentally released 40 grams. How much will remain after 60 years? Okay, so that'll be the A naught, right? So, okay, let's say that the initial size was 40. Okay, so if the initial size was 40, then how much will remain after 60 years? Okay, so we want to be able to calculate this quantity right here. Now, just a reminder, make sure you do all of this. Don't do all of this in one shot, right? Don't do 40 times 0.994240 to 60th power. Okay, some calculators can't handle that order of operations. Okay, so I recommend doing this one by one. So do this part first. Okay, do 0.994240 to the 60th power. Hit enter, and then multiply that by 40. Okay, and by doing so, you should get something about 28.284 and some change here. We'll just round this. Okay, so we'll say 28.28 years. Okay, so that's how long it'll take. Oh, I'm sorry, not years, right? That's the grams. Okay, that's how much will remain after 60 years here. Okay, so we'll call this grams. And so then the third question is, well, how much will remain after 300 years? Okay. So this was the second problem here. So the third problem then is, okay, let's do the same thing. We know that we started out with 40 grams, okay, and we know that this was our constant, okay, 0.994240, but now we want to raise this to the 300th power, right? Okay, so similarly, make sure you do this part first, 0.994240 to the 300th power. Right? Don't round it, don't clear it out. You should be able to just hit times 40 after that. Okay, and this gives us 7.07 grams. Hopefully that makes sense, right? Every 120 years, half of this remains, right? Now I want to mention, right, that this is not a linear. So after 60 years, it's not going to be. You don't want to look at the 60 compare it to the 120. Don't do anything about that, okay? Okay. But after 120 years, half should remain. And after another 120 years, half of that amount should remain, so on and so forth. Okay, so I think these numbers are about right.